Good morning, good afternoon, and welcome. Today's webinar is the third in a series organized by Alberta Agriculture and Irrigation and in partnership with the Canadian Dam Association. I am Jenna Montgomery, Chair of the CDA's Professional Development Committee and a Senior Dam Safety Technologist with Alberta Agriculture and Irrigation. I'm pleased to have you join us today for this webinar on a variety of surveillance techniques that utilize advanced technologies. The CDA, the Canadian Dam Association, is a non-for-profit national forum for individuals and organizations to maintain a discourse on the advancement of dam safety principles and practices. The vision and mission of the CDA reinforces the value of safety and competency in the field of dam safety. CDA members collaborate to develop guidance such as the dam safety guidelines and technical bulletins. Volunteers also develop, plan, and deliver workshops, webinars, and the annual conference. There are always opportunities to volunteer with the CDA, and please do contact the CDA if you are interested. Membership is open to individuals and corporate groups and must be renewed annually. Student memberships are also available. Please see the CDA's website for more information on the benefits of membership. Today's webinar sponsor is Beaded Stream. If you are interested in sponsoring future webinars, please contact the CDA. Before we introduce you to our presenters, I would like to draw your attention to the Q&A function at the bottom of the Zoom window. Please use this to submit your questions. We will have 2 Q&A sessions during today's presentation, and I'll read out those questions to our presenters to answer. I now pass things over to Mohan Acharya. Mohan is a senior dam safety engineer with Alberta Agriculture and Irrigation, and he will introduce us to today's presenters. Mohan.
Thank you, Jenna. On behalf of Alberta Agriculture and Irrigation, it is my great pleasure to introduce today's speakers on this evolving topic of leveraging advanced technologies for dam surveillance. We have Mike Davis, Amy Schwerd, Amy Sneddon, and Andrew Bellis from Stantec Canada and US offices. Mike has over 15 years of international experience in planning, procuring, installing, and managing instruments for mining and heavy construction works. Mike's experience includes adapting existing technologies to enhance surveillance and monitoring techniques, geotechnical performance monitoring using discretized sensor network, automated systems, GIS-based inspection and monitoring systems, and INSAR. Mike has also provided ongoing training for analysis and interpretation of advanced techniques for SMARCO staff for the surveillance of Fundao Dam. Today, Mike will present the first case study explaining the application of GIS for dam monitoring and surveillance. Our second speaker, Amy Schwerd, has over a decade of experience in dam safety, geotechnical studies, and instrumentation programs across Canada, New Zealand, Australia, and Laos. Amy has been involved in the design, implementation, and review of instrumentation and automated data acquisition systems, the development of surveillance manuals, and preparation of technical guidance document for the World Bank. Today, Amy will give us an overview of available advanced technologies and discuss a case study on digital monitoring of small dams. Our third speaker, Amy Sneddon, has over 15 years of experience in instrumentation and monitoring of a wide variety of structures with a special passion for embankment dams. Amy has led the investigation and instrumentation installation at many dams in Alberta as part of ongoing monitoring and remediation of aging infrastructure and new construction work. Today, Amy will discuss the application of advanced technologies in dam instrumentation with a case study of a new dam that is under construction in Alberta. And our first speaker today, Andrew Bellis, has over 2 decades of diverse experience in dam and instrumentation design, construction, numerical modeling, safety reviews and audits, forensic studies, and senior leadership. Andrew has worked over a dozen countries around the world and also an engineer of record and construction manager for the ongoing Springbank Dam project in Alberta. Andrew is going to present the background portion of today's webinar. With that, take it away, Andrew. Andrew, you are muted.
Thanks for that, Mohan. I just realized that teething problems. So thanks, Mohan. I really appreciate that. Yeah, so I'm Andrew Bayliss, and I'll be providing the introduction for this presentation. As you can see, my colleagues will be taking over, and they'll be doing the majority of the work today. And I just really want to take a minute to thank the team for their hard work on preparing this presentation. I hope it's enjoyable, and I hope the audience will learn a lot from today. So in terms of the agenda, we'll provide a quick overview in terms of obviously the scope of the presentation, some of the guiding principles that we work to in dam surveillance, talking about some of the current surveillance practices, and then we'll move more into the advanced technologies, where my colleagues will spend a bit of time just talking about some of the technologies out there, how we use them, how we apply them, what are the pros and cons, and so forth. And then we'll move into a question and answer session. Again, this was kind of like the structure that was followed previously. And then my colleagues will take over and move more into the case studies, and we'll be talking about 3 case studies as part of this presentation. Closing marks, then moving again into a second question and answer session as well. Next slide, please. So in terms of the purpose and the overview of this presentation, again, we want to build on the previous presentation that was presented by AEP several months ago, where Tetra Tech and RST talked about some of the monitoring surveillance technologies that are using. So we really want to build off that a little bit. So the purpose would be to educate dam safety specialists about the continued improvements in dam safety monitoring. We've deliberately framed this presentation in the context of earthfill dams, concrete spillways from Alberta, but as you're all aware, a lot of this discussion can apply across Canada or globally. In terms of the actual presentation, we will look at the principles of dam surveillance, we will look at continued and current best practices, give those examples, case studies, and have a period of reflection. And lastly, I just want to really want to emphasize this. We do talk about proprietary technologies, but for the purpose of this, we are software neutral. We're not endorsing any particular type of software supplier or manufacturer or so forth. It's just obviously we really want to kind of educate the industry as to some of the technologies that are out there. Next slide, please. So I've just got a couple of slides that just talks about the guiding principles of dam surveillance, how we tie that back into the Canadian Dam Association guidelines. I'm assuming everyone's kind of familiar with some of these principles, and I don't really want to kind of go over them. But as you can tell, that some of our defining ones are tied in principle 1A, 1B, principle 2A and 2B as well. And it just kind of gives you the level of expectation that is needed in terms of risks, in terms of consequences of dam failure, and how we tie in surveillance as part of the OMS manuals, and how that ties into operations, and how we document it and so forth. Next slide, please. So in terms of like current surveillance practices, obviously there's a lot of documentation available within the industry. Because we are talking about this from the context of Alberta dam safety. We do tie back into the Alberta Dam Safety Directive, and also the Canadian Dam Association guidelines and the relevant technical bulletins as well. There's also the ICOL documentation, which is ICOL Bulletin 158, which provides a lot of really good content. And as everyone else is aware as well, there's a lot more documentation out there, like monitoring dam performance, which was an ASCE document, and various other bits and pieces. So in alliance with CDA Principle 1A, we do talk about the best practices, and we do obviously tie that back into the fact that every surveillance activity should have a purpose. It should tie into the potential failure mode and so forth. And on the right-hand side of the screen, there's a plot that we've extracted from ICOL 2018, which is the surveillance guide. And that kind of gives you the framework as to monitoring, visual inspection, checking, testing, how that ties into the objectives, and what is the overall, and how that ties into the overall assessment of dam safety. Next slide, please. So in terms of like continued improvement in surveillance practices, they need to be obviously improved upon. I mean, there was a need to increase information in the project database as the project evolves. There will always be new issues. There will always be kind of new failure modes that could be identified at any time. And we also want to reflect the fact that there's many dams in Canada in Alberta and throughout the world as well, which are kind of reaching the end of their kind of design life as such, and they are aging infrastructure. They are kind of aging assets that do require a need for continued surveillance, improvements in technology, and so forth. And as we recognise, improvements in technology are being undertaken on an ongoing basis. Even in my last 20 years of experience, the kind of leaps and bounds the industry has moved towards in the last 20 years has been pretty remarkable. And it's obviously going to get even more when we move into more artificial intelligence technologies. We have more processing power, we have more digital technologies as well. And obviously the scale of these technologies move into a more usable and more palatable kind of scale. And next slide, please. So we like this. We've got this slide here from one of my colleagues' papers, and it just talks about the range, the practical application of where we are in terms of advanced technologies, and it kind of ties back into a lot of the growth that we've seen in that last 20-year period. You can see on the y-axis we have the lag time, and on the x-axis we have where we kind of sit in terms of our modern practices. Obviously, in the past. Moving towards the future. And as you can see, we've moved into this kind of period now of using fully automated systems, using new technologies and so forth. And the curve is moving down a little bit, and we are moving towards more of that kind of intelligent systems, and in an ideal world, obviously moving towards more of that predictive analysis. And again, we'll be talking a little bit about that in this presentation as well. Next slide, please. So in terms of lastly, before I hand over to my colleagues, what are advanced monitoring and surveillance technologies? Obviously, we've used that as the title here, but I mean, again, there's a lot of different topics that we can put into this presentation. So for the purpose of this presentation, we decided that these are tools to increase our understanding of dam performance, and they can include efficiencies, improvements to data management. They can kind of decrease the processing time, but also increase the amount of data that can be obtained at any one time. And this allows obviously continuous management, big data, etc., etc. We also recognize there's improvements in reliability, instrumentation as well. We recognize that there's new imaging technology that we can utilize on multiple facets of the facility. We also want to mention that artificial intelligence is there, kind of simmering in the background, and it's something that will be increasingly used as the dam industry moves forward. But lastly, a couple of points, and I think this ties back into obviously some of the fundamental principles of dam safety management. They're only as useful as they're applied. I think we all kind of recognize that the knowledge and the experience of a dam safety specialist cannot be replaced, and this forms part of the tools, and that they should be carried out to basically reduce uncertainties around the potential failure modes. So with that, I'm going to hand over to my colleague, Amy, and for the rest of the presentation. Thank you.
Thanks, Andrew. So today I'm going to talk about some data management technologies and in dam monitoring systems. So in the last 10 years, data management systems in dam safety management have been developed to really aid dam owners in managing their dam safety surveillance programs. So these systems help manage large amounts of data, which is really important, as most dams in Canada have 30 to 60 years worth of data or more, and a large well-instrumented dam can have hundreds of instruments installed. So without a good data management system, the surveillance review can be really difficult and time-consuming. So data is really typically presented in a nice visual format for us to see. So you can see it in a graphical interface with either 2D or 3D dimensions, where you can usually point and click into a dam site. And then again, you can see the dam site visually represented either in 2D and 3D. You can also develop different types of graphs for multiple forms of interpretation, and those can be grouped. You can also program alarms and alerts right into the system. So if an instrumentation or a piezometer, the alarm level is reached, you can set it up to send you an automated text or email if that is reached. And if it's fully automated system and it's after hours or in the middle of the night, you would get that alert right as it happens in real time. These can be accessed on multiple platforms, including your phone or tablet. So if you're out in the field, it's really handy. Even if you're not out at the site to do a dam inspection, sometimes we're out there for other reasons, but you might notice something. And if you have all the information right on your phone, you can pull it up and everything's right available. And it can just really help get that data all together when it's needed. And then also it's web-based or desktop-based for when you're in the office. They can also really reduce your processing times. So it takes a little bit more time to develop the database system. But once it's fully developed to whatever the owner's needs are, you can really set it up so to really reduce that surveillance reporting time, either monthly or annually. You're just importing the data and you can set it up to automatically run that report. So there are several suppliers that are known to specialize in dam safety monitoring systems, as Andrew mentioned, for software neutral. The important thing is that the data management system should be configured on an individual basis for that dam's identified failure modes, the dam history, the construction, all that information for what you're doing. And then you also have the ability to monitor for impact signs of failure modes. And these systems can also be developed on an individual basis and built in-house. You just need the correct IT support. So a little bit on digital inspections. So having an experienced dam safety professional's eyes on the dam is a critical component in a dam surveillance, and it really forms the effective backbone of a dam safety management system. So inspections and surveillance, they were discussed heavily on a CDA webinar that took place in February 2021. So I'm not really going to get into the details because that webinar is available online. But on the topic of advanced surveillance, there's really a drive towards getting the digital collection of inspection data. So there's been applications or programs that are available or again can be developed in-house to carry out digital inspections. So digital inspection forms, just like a data management system, can be set up with a lot of flexibility. On the screen, you will see a digital inspection form playing through, but you're able to take georeferenced photos right on site as you're carrying out the inspection. You can enter out that comment right on site. You can set up the forms to walk you through each step of the inspection. Different dams, if you have multiple dams, different dams can be set up with different forms. So you're walking through the same thing every time. If there's any identified seepage issues at a known dam, you can incorporate that into the inspection sheet and say, this is what we need to check. You can also import or set it up to have automatic calculations. If you're taking a water level reading, you can set up automatic calculations. And then you can also set it up so anyone can access it with a guest access as well. It's kind of up to the owner on what they prefer, but if a consultant is coming out to do an annual engineering inspection or dam safety inspection, you can set them up with an access to carry out the inspection form right through digitally through the same form that the operators use as well. So again, it's just really flexible, and these inspection sheets should be developed maybe not on the most advanced surveillance, but what is right for you and your dam and really identifying the important risks. So this is just an example of a canary multi-logger. This is used by the Alberta government dams, and you can this is just to show the platform. We can visually see on the screen, we have the map view where you can see all the dam assets available. These are color coordinated, so the green dots would represent that all the instruments are within the normal operating range. The red or the yellow dots would indicate that there's potential for operating outside of the normal range. You can then point and click right into a specific dam site, and then you're really getting that 2D or 3D visualization of the dam right on the spot. We can see here that we have instruments installed and the emergency spillway and fuse plug, the spillway itself, and the embankment. We can also see that red mark on the embankment, and that would indicate that there's an instrument within the alarm levels in that area. We can further also click in right into the spillway area and really see the exact locations of those installed instruments, and they are color coordinated where the blue titles are representing pore pressure monitoring instruments, and the red titles are representing deformation instruments. And then, as I mentioned, there's really multiple forms that we can set it up for that graphical review of the instrumentation. We can visualize them grouped by cross-section or by area or by type. And it's multiple on how you want to interpret that data. So you can really interpret data in different ways that maybe you weren't doing before. So DAMSat. DAMSat is a monitoring software which provides regular dam monitoring using satellites. It uses a combination of INSAR and GNSS to monitor movement. And also there's in situ displacement sensors to really monitor those abnormal behaviors such as movement or seepage. It also includes optical satellite data with pollution indicators. And it can also incorporate 10-day weather forecasts, which can be incorporated and tied to the hydrological numerical models if they're incorporated into the system. So you can really assess if there is a big storm coming. You can actually have that in the system. It will get the forecast and go into the numerical model, and you can assess what the downstream levels would be in a potential failure. So it's a really unique tool. The interface does include a number of modules, which are shown on the screen above here. So if you were to log on, you would get the general information, alerts, visualization, movement detection, the pollution indicators. You would look at the hydrometric forecast, and then you can also tie into emergency planning as well. Okay, now I'm going to get into a little bit of topographic mapping technologies. So there's been advances in topography mapping in recent years that can really provide deformation monitoring in ways that we were not previously able to. We're able to get increased resolution and precision using these technologies, which have the capability for us to assess the detailed displacements over a large area as well. And we can also have scans that are carried out at increased time intervals for increased levels of monitoring. So today I'm going to discuss various types of new topographic technologies, and it's definitely not a conclusive list by any means. I'm not a saleswoman. I'm not going to get into any of the major details on these technologies, and we are very neutral on anything that I'm going to be presenting. But I just want to go over some of the main points of some of the available technologies to maybe give you an idea of something you may or may not have heard of before. And then you can think of it if this is a technology that you might be able to use at a project in your dam to lower the risks. So satellite INSAR, it's a remote sensing technology which is capable of measuring ground displacements with 1 to 2 millimeters precision per year. It has longer wavelengths, which allows the signal to penetrate through cloud cover, fog, rain, or dust. However, the snow cover is limited, the effectiveness of the scanning. Because it measures along a line of sight relative to the satellite orbit, it can have a restricted detections on steep slopes. So that's something to keep in mind if you are planning for a dam inspection. And it uses a SAR technique to measure displacements over 2 time periods. So 3VG is a proprietary INSAR system, which is capable of remote monitoring millions of data points and near real time. I'm not going to get into all the details of 3VG, but you can see the image of the platform on the sidebar here. And also they just have experience carrying out inspections and sort of topographic mapping for a lot of dam projects. You can just see an example here of an embankment survey. So ground-based synthetic aperture radar is a remote imaging system which is capable of obtaining deformations that are less than 1 millimeter, and it's proven to be a reliable remote sensing tool. You can just see the setup on the side here. So you would have the radar sensor, the scanning rail, it would be connected to a power module, and then you would have the laptop available for data acquisition. Terrestrial laser scanning. It's a contact-free measuring device, and it does require an unobstructed line of sight to carry out the survey. So to carry out a survey for a dam site, you typically require to set up this laser at multiple vantage points. around the site, and then the scans would be combined from each vantage point and referenced in spatial coordinates to using survey points. And then it also has built-in cameras to allow for automatic texturing. So using the geographic coordinates and that the photographic scanning, you really can develop a nice 3D model. So structure from motion is a unique tool that utilizes a series of 2D images to create a 3D component. The images are overlapped from multiple positions using a photometric workflow. And the images are first undistorted using key point detection, which are used to identify key features such as a bedrock outcrop. The key points are matched and created as discrete point in 3D spaced. And then there's a distribution key point that matches, which is used to calculate the position and orientation of each image in 3D space. And then those matches are projected to create a 3D visual model. So I just have an image here that I found in a previous paper of the 2D to 3D SMF output. So it's a really unique tool that can be used in dam surveillance. So unnamed aerial vehicles. So UAVs, they're becoming more and more common, not only for professional use, but also in recreational use. But they can be incorporated into dam inspections to inspect remote or restricted areas. And then they can incorporate laser scanning as well to develop a DEM. They really allow for a more detailed review of the inspection. So if you're having a flyover inspection and you have that video on record, you're really seeing, you have that record and you're getting the full site. So if you're carrying out a walkover inspection at a later date and you notice something that is different, you can always go back and see that right on the spot. You're having and it's a cost-effective technology as well. To carry out an inspection for a large dam, you're looking at can typically carry it out on a 2-hour survey. And then the cost will depend on the drone that is used, but costs that we're seeing are typically $1,000 to $3,000, including data reduction, to have a survey done. And the cost depends on the area and the drone used, but it's still really cost effective. The photos that I have on screen are just photos of an active construction site for a dam in Alberta that we're working on. We're having weekly surveys with drone photogrammetry carried out that are tied to control points to develop a point cloud model. So having that point cloud model, we can develop a DEM, which we can then use in AutoCAD. So it's a really effective tool for weekly progress tracking. Not only are we getting that visual photographic record that will have long-term, but we're getting that digital elevation model that we can tie into the instrumentation ADAS system to really review the excavation rates and the placement rates and how that affected the instruments to respond. And that will be on the ADAS system for long-term monitoring. So AutoSpecs, it's a proprietary damage assessment software. It uses acoustic frequency data to automatically map and quantify damage such as cracks, spalling, and delamination. It allows users to visualize and assess defects over time. It uses a series of optical imaging, infrared imaging, and acoustic signatures that are able to look for defects that are up to 1 millimeter, 50 millimeters, and 200 millimeters into the concrete. So you can get that into the concrete data to assess. So digital outcrop models are something we're using more and more in our advanced analysis. They're really powerful tools for 3D geological analysis of existing dams on bedrock. They're really best suited for concrete dams on bedrock with numerous exposed outcrops. And they're intended to create a digital model with sufficient detail to form a practical, usable duplication of the real foundation. So you're going to map the exposed outcrops around the site. And then you can extrapolate between the outcrops to really build the full scale model. You then can calibrate this with boreholes, construction records and drawings. The more information you have for calibration, the better. One thing to note when you're creating a digital outcrop model is you're using the assumption that the rock mass characterization from the available outcrops is representative of the large scale site. So that's one limitation, but I think we can still get a lot of really good information from it. And these are just some nice images of digital outcrop models that have been developed. And with that, I am going to hand it over to Amy Snedden to talk about instrumentation.
Hi, so good morning, everyone. If you bear with me while I try to share my screen. There we go. Hopefully everyone's seeing it now. Okay, so I want to start just with a brief discussion of instrumentation. This was previously discussed, at fairly great length by Savannah Herman of Terra Insights in the 2021 webinar that we've referenced a couple of times. But today I do want to focus on two advanced monitoring options that are both the, two advanced monitoring options that are available right now to monitor for deformation and seepage. And these are the shape accelerators and distributed temperature sensing systems. Okay, so first with the shape accelerator or the SAE. So for anyone who's not familiar with this product, it's essentially an update to the traditional slope inclinometer that I think most of us would have used at some point in our careers. Where it really differs though, is that where with the slope inclinometer, you would go out, you would lower down the reader instrument and get that one discrete data point on that one day. With the SAE, you actually get real-time monitoring information, both of horizontal and vertical deformation. But one of the really cool applications for it is that you can also apply it in an arc for monitoring of something like convergence in a low-level outlet. So these are accurate to within 1.5 millimeters on a 32-meter array. And on that, on your arrays, you can tailor specific zones to focus using silent segments. So those silent segments aren't taking any readings. They aren't sending any information to you on whichever reading system you're getting your information. You're just getting information from those active zones where you've tailored to monitor. One of the key advantages that I've found in my practice is that the SAE can be retrofitted into existing casing. So if you have the traditional SI on site and you're a little bit concerned about something, you've identified a potential failure mode and you feel like you really need that real-time monitoring to give you that data to make proper assessment of what's going on, or even to give you some comfort that nothing awful is happening, you can install the shape accelerator within that existing casing. And again, for me, the key benefit with that as well is if you're already concerned about slope stability, is this a structure that you really want to be drilling within? So you're kind of avoiding the risk of drilling as well. So really that for me is one of the really great qualities of the SAE. Disadvantages to them as they are, as you can imagine, because you are installing some form of casing to then install the SAE. It's more expensive than a traditional SI to install. And really when you're thinking about selecting them, it's up to the engineer to decide, hey, do I really need this real-time data, or is that one discrete monitoring point enough? And is it worth that extra cost to get the real-time data? So I think there are definitely advantages that justify the cost, and it really depends on the application. They also are fairly tricky to install. Some improvements have been made where it used to be the instruments were incredibly heavy and you needed some machinery to hold the reel to unfurl into the holes. But as you can see from my photographs here from some recent installations, it has become fairly simple for a two-person team to install. As I mentioned, they are installed within casing too, and a kind of unique thing is you have to compress the SAE within the casing. And if you don't do that properly, it can present later in your readings as drift or some ghost movements that aren't real. But you can then go either correct that via the software that you're visualizing in by re-zeroing the SAE, or you can simply go out to site and recompress the instrument. Which does bring me back to an advantage, which I forgot to mention. Say you install an SAE on site and you're doing your real-time monitoring, but you actually find, I'm not getting useful data here. I don't need to have these multiple data points. Once a day is enough. You can actually remove the SAE and reuse it in another location where perhaps you are seeing movement or you do feel like you need that real-time monitoring. So it's quite a flexible system. So these are quite widely used in Alberta dams, and there's far too many to name, but kind of later on in the webinar, I will be discussing one case study where we've applied the SAE to an active construction, the active construction of a dam. Okay, so on to a seepage monitoring system that uses advanced technology, and that is the distributed temperature sensing system. So DTS works using lengths of fiber optic cable that are trenched within the ground and are able to detect variations in temperature. So these cables, can be up to 90 kilometers in length from one hub, depending on the system that you are using. The length does vary, so I would encourage you for your individual uses to connect with an individual supplier to figure out which system works best for you. But the system works using the principle of the Raman effect, where wavelengths are influenced by external forces. In this case, we're looking for changes in temperature, so it's temperature that's influencing that wavelength and then is then picked up by the system. So it can accurately identify very small variations in temperature. The manufacturing information suggests it can go as low as 0.01 degrees centigrade, so incredibly sensitive. And then it can locate those changes at a very precise location along the fiber optic cable. But why do we care about temperature variation? So the unique thing with this is the product is using temperature variations to correlate to seepage flow. And then this has been successfully used across many dams in Europe and has been adopted in dam monitoring guidelines in Sweden. I have been talking to some manufacturers recently for possible application to a dam in Alberta, but as far as I'm aware, there aren't any air-filled dams in Alberta that currently use this technology, although it has been applied to mining sites for leakage detection. Okay, so building on DTS technology, SensorNet have also now developed a special purpose optical cable for dam monitoring, which is the distributed temperature and strain sensing system. So it's kind of in the name, but as you can imagine, the cables are monitoring for both change in temperature and change in strain. So it's doing this by using 3 separate measurements: temperature compensated strain, strain without temperature compensation, and dynamic strain distribution. And it's taking these readings based on the same principle as I'd mentioned before, where an external force is impacting wavelength. In this case, it's looking for strain and temperature. So the changes in strain are then used to estimate deformation along the fiber optic line. And these cables are limited to around 10 kilometers in length, although I do believe that SensorNet are working to increase this coverage. There have been 2 successful trials of the system completed in Sweden that were reported on some case studies in SensorNet's website. And I would encourage people to read those case studies. They are incredibly interesting and give a good background on the product. But the first of those 2 trials was unsuccessful. I think there was some damage to one of the cables and the strain sensing wasn't operational. So some tweaks were made to the system. The cable was made more rugged. And then the second trial was a success and predicted movement and seepage in line with existing instrumentation on the site. And it is considered appropriate for use in air-filled dams now. Okay, so a data management system that's related to the DTS is XCT. So this is a product which, similar to the ones Amy discussed, are exporting real-time data from site and then presenting a visualization of that data. So it presents both a visualization of the temperature and of the interpreted flow data. So I think that's the key piece with this one, is it is showing that interpretation of data. So the live data can be reviewed with no need for mobile equipment or anything. It can be used via a web interface. So there's no need for investment in any additional equipment other than the installation of the DTS system itself on your site. One of the nice things is that data from XCT can be exported into an existing data management system. So say if you're using something like Canary on your site, you can export data from XCT into Canary so that you can see all of your instrumentation data in one place. As with something like Canary, you can also set alarm levels in XCT so that notifications can be sent to the appropriate people and the proper procedures can be put in place. And that brings me on to, I think, a really interesting portion, or a really interesting, discussion point on DTS and DTSS systems. As I mentioned earlier, we don't have any installed in existing dams in Alberta, as far as I'm aware, and I think one of the key reasons for that is constructability. So as you can imagine, because it's a length of cable, there does have to be some level of trenching involved to install this system. SensorNet have done some trials with various different applications of installation. So you can see some design examples here, but they ran trials installing DTS systems and a combination of both within a dam crest, within a toe berm, and within a trench at the toe. Through those trials, they did find that they were successfully getting data that correlated well with instrumentation that was already on site. So there are various different applications that can be considered for these. But I think when considering them for use, you do have to take a beat and think, do I need this real-time data? Is it worth potentially excavating a trench within or close to my dam? Or would something non-intrusive such as geophysical investigation on an ongoing basis be enough? So again, it's similar to the discussion between the SAA and the SI, where it's really about selecting the right tool for the job and comparing that with the level of risk that you're taking when you choose to apply one specific technology. Okay, so looking to the future of advanced technologies, as Andrew mentioned, we're really in the early stages of adoption for artificial intelligence, but we have seen some advances recently that are applicable to dam engineering. And after I've given a general overview of what artificial intelligence is, I'll get into that. Okay, so I feel like this is a subject that when we say artificial intelligence, it's not abundantly clear what we're talking about. So I just wanted to give a brief description of what we're generally referring to. So artificial intelligence is a computer system that's able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. Where we're seeing applications of artificial intelligence right now is typically the subset of AI machine learning, and that studies computer algorithms that improve automatically through experience. So some examples of that we'd see in the world right now would be things like self-driving cars or the assistants that we have on our cell phones, such as Siri. So one example I did find that wasn't directly applicable to dam engineering, but is somewhat dam engineering adjacent, is what NASA is doing with AI right now. So NASA is using AI and machine learning to sift through years of data and imagery to rapidly and efficiently find relationships that would be impossible for the human eye to detect. It's also doing this, it's also sorting through years worth of data in a short span of time, which would really be impossible for a human being to do. And I guess one of the exciting opportunities I can see here is being able to avoid sifting through years of instrumentation data when doing a dam safety review. I would love it if AI was doing that automatically for me and looking automatically for any possible trends that could indicate that it needs further review by the engineering team. So NASA has made their code freely available to engineers around the world so that we can ourselves develop new uses for those algorithms. And I think that's really issuing a challenge to us to start developing the next generation of advanced technologies in dams. But there is one available right now that I'm going to talk about. So WaterSat Geospatial AI is a dam monitoring product that has two key modules that are directly applicable to dam monitoring, and that is the dam monitoring module and the urban change module. So the dam monitoring module remotely monitors surface movement and change in vegetation on site. And in this case, change in vegetation is being used as a proxy for seepage. So it would be the assumption that increased vegetation equals increased moisture, which equals increased seepage. So this is powered using INSAR and satellite data, which dates back to 2016. So there is a backlog of data available that would then be reviewed by AI algorithms to detect trends, patterns, and outliers that could indicate areas of concern. And I think one of the key benefits here for a dam operator is that you can target specific areas for review, investigation, remediation even, or just further instrumentation to confirm what the WaterSat module is picking up. And that really allows you to focus your spending in areas of increased risk. Where it becomes really powerful is if you apply that module across an entire portfolio of dams. So you can really see where your risk is, develop that risk profile, and then target your spending accordingly for where you really need to do the work in a given year. Then the urban change module, it's also a remote monitoring system that's been powered by that satellite data and reviewed by AI algorithms. But this one is actually looking for development within the inundation zone. And I think that provides valuable insight to dam operators when looking at emergency planning and reviewing emergency planning documents, because you can see immediately if there has been any change downstream of your facility and if there's any need for update. And similarly, when coming to do consequence classification review, that information's right there without your consultant having to sort back through years of aerial imagery to see if there has been any changes. So as you can imagine, this is all presented on a dashboard as well, and you can see some examples on the screen with the highlighted areas that are slightly darker orange, showing areas of possible increased risk. And then this can be fully manipulated and filtered by the user as well. And again, as with the other products that we've talked about, it's available via a web browser or also on tablets and iPads. All of the information is also easily exportable into PDFs for inclusion in reports. So again, when we're doing things like emergency planning or consequence classification review, all of that information is there and can be attached to documents so that you have that chain of custody of information. Okay, and with that, I'll hand back to Jenna to moderate our first question and answer session.
Okay, thank you. We do have a few questions. The first is drone photogrammetry. Sorry about that. Good enough. Is it being utilized for quantity survey work on the active dam site? And any of you can jump in. Maybe you want to turn on your cameras and audio.
I can answer this one, Jenna.
All right.
So yes, it is. We've been using drone technology extensively throughout the project. We use it to define the quantities, check quantities. We reference this consistently with what the contractors are giving us. And we use it to derive quantities for payment and so forth. There's other applications as well, but for the purpose we're using it on that project, it's served its function and has made our cost estimation and our cost progress estimates a lot more streamlined than in the past.
Okay, thank you. The next question is about the monitoring systems. Are they effective for snow-covered dams in wintertime?
I think I need a little bit more information on the question. It would depend on the type of sensor type. The monitoring system in the sense of database management, that would be reliable year round. And in colder climates, you would have obviously batteries that you would have to be checking and making sure that. As for snow cover, it kind of depends on how you're carrying out the survey. Some methods would be and some methods wouldn't be.
With the systems that use 3D models, where are they shared and stored online?
So I can maybe, sorry, Amy. I was
Go
going to
ahead,
say
Amy.
I can maybe speak from the construction experience. We are using a project SharePoint. We don't have any smart system out here on site right now for doing that. So they're stored on SharePoint, which is easily accessible by the project team out here as well as the client team. We have a shared system. But unfortunately, nothing too advanced when sharing those right now. Andrew, I don't know if you want to add to that. I see your camera coming on.
Yeah, it's coming on slowly. I think it depends as well. It depends on the framework and the system architecture as well of the client or the dam owner, and so forth. I mean, I don't want to dwell too much into obviously IT because that's kind of definitely outside my skill expertise. Mike, maybe I'll be able to add something to this, but it depends really what kind of systems are in place already within the client and within their existing dam safety system. Whether they have a mature IT system, whether they have multiple backups, is there a cloud system involved, et cetera, et cetera. So it's not really an easy really an easy answer as such, and it just depends on a lot of practical issues.
Okay, thank you. So there was a question about INSAR in relationship to more traditional land surveys and total station surveys. Now the INSAR, that can't replace those traditional methods, is that correct?
Yeah, I'll address this question. That is right. We're looking at INSAR to view differential movements or relative movements of the Earth. It is not a technology that can provide us with topography or a digital elevation model. So it does not replace LiDAR or drone-based LiDAR or those type of technologies as far as mapping of the ground surface for absolute position.
Okay, thank you. Now there's a question, can we use these techniques to monitor or in the monitoring of RAG phenomenon inside powerhouse buildings?
I think we need a bit more information on that.
Okay, so I mean, if you can provide a bit more information, we can get to that question later on. Now, is there no 3D model image hosting service that you know of?
I mean, yeah, I think I'm trying to understand a bit more about the context of the question here. I mean, obviously, we're familiar with Sketchfab. There's Leica CloudWorks, there's Cyclone. There's a range of tools available. Obviously, it depends on what the application is. Depends on what your budgets are. Depends on your organization. Do you have enterprise agreements with Bentley, for example, or other entities? So there's multiple tools to be able to visualize the 3D models.
Okay, thank you. So back to this question. So RAG means alkali aggregate reaction. So are any of these techniques suitable for monitoring alkali aggregate reactions?
That's a good question, and it's something that we can probably provide a bit more information on in the second period as well. I'd have to think a bit more about the context of the location and so forth, and where that place is.
Have you had much confidence with drone-based surveys of dams with rock fill shells and looking for changes in slope, shape, sinkholes, etc.?
Not drone-based specifically, Jenna, but I'd say INSARs are a pretty powerful tool for looking for that from my experience.
Yeah, I mean, it also depends as well on what kind of confidence you're talking about. And I think it kind of ties into where the site is. Because obviously, if you've got a sinkhole in your dam crest or your dam slope, you kind of, your visual inspections by the person on the ground should be able to pick those up. Obviously, the other things come into play like vegetation and so forth. Maybe if the site's a bit more remote, maybe then you'll bring in that drone technology. But it's certainly one of the things that you can use but not the only tool you can use to obviously determine sinkholes.
Now this question is for Amy Sweard. You had mentioned you are seeing drone surveys at $1,000 to $3,000 price range, including flight time and processing. Does that include ground truthing as well? What kind of data resolution are you seeing with these drone data surveys?
Yeah, well, the $1,000 to $3,000 was what I mentioned on the weekly surveys that were getting carried out at our active construction site. And as Andrew had mentioned, we're finding that the resolution is reliable enough to be relied on, and we're cross-referencing that that with survey data that we're getting from the contractor as well. And so yeah, it is providing that good resolution for that price point.
Okay, and just one last question before we get back to the second part of the webinar here. This is in regards to data management systems. Do you know of any dams that are being used as active demonstration sites, essentially, where these systems are being used, that people can see them in action, or any sort of advice for people to see those systems being used, connect with dam owners that are using them, that sort of thing, to help people make decisions?
That's a good question, and it's not really an easy answer as well. I mean, there's obviously a lot of examples around Alberta and British Columbia within the industry as well. In terms of, sorry, Jenna, did you just remove the question there or not?
Well, it's in the answered section.
That'd be right.
Yeah.
Yeah, I was just looking at it, then all of a sudden I was looking at a different question.
No, and it's kind of combining a couple of questions.
Okay.
I do know that, like, from our experience, like, vendors are always willing to demonstrate their software and their applications, and they can sometimes connect you with other dam owners that are using it. At CDA conferences, they always have the vendor booth set up, and I think, and connecting with dam owners, seeing what they're asking, what they're using, that can always help you see those things in action.
Right. Okay. Now I can see the question, I think.
Okay.
But yeah, I think you've answered it right there, Jenna. There's a lot of examples there, but it's not a simple kind of test dam site or anything. There's a lot of active dam sites throughout Canada for hydroelectric, water, mining, and so forth, where a lot of these technologies are employed. So I would encourage you to speak to the dam owners, the dam operators, the consultants in question, the suppliers that are involved, and to see if they can provide these examples. Again, we've really tried to be supplier, software developer, manufacturer, distributor neutral. I'm pretty sure there's a lot of people from the suppliers on board this today, and I'm pretty sure they'll reach out to you afterwards as well.
Okay, well, thank you. So that concludes this first Q&A session. We'll get back into the presentation, and I will remind you, it is with multiple presenters. If you can specify if your question is for a specific presenter, just include their name at the beginning of your question. All right, and I'll pass it back over.
Perfect. So now we're gonna take a step through several case studies. The first one being implementation of a site-wide geographic information system, or GIS. Some of this information was presented previously at the CDA annual conference in 2022. The information comes from a paper written by myself and several colleagues within Stantec, as well as our colleagues at TransAlta Centralia Mining. So I'd just like to thank TransAlta for allowing us to share this case study to further the development of and use of technologies across the dam monitoring industry. This is a great success story, and hopefully all of you will agree by the time I'm finished presenting these slides. So today we're going to talk a little bit about the Centralia mine in Washington State. This site is characterized by high precipitation. It's in the Pacific Northwest, and also high seismicity. So as far as dams go, one of probably the worst possible locations for a dam to be. These dams are owned by an Alberta-based company, again, TransAlta, and Stantec is the engineer of record for 6 high consequence dams Those are all earthen embankments, 2 water dams, and 4 tailings impoundments. So just setting the stage here, we're talking about a GIS developed for tailings and water dams. A lot of what you're going to see is applicable to sites all over Canada. And a lot of the information that we're going to be showing and sharing here is publicly available data that we've aggregated into our GIS system. A couple of interesting characteristics on the site. There's a complex regulatory environment. There are several regulators at this site, and the design events for the earthquake and the precipitation are different. So some of the guidelines for design are stipulated by one of the regulatory agencies, and then some of the other dams are superseded by the other regulatory agency. So keeping things straight here and making sure that all of our information and data is organized in a very logical way was very important for this work. So in 2019, we completed a dam safety review of the dams on the site and found a few areas for improvement, analyzing and interpreting performance monitoring data, focusing the inspections on relevant items, potential failure modes, and distilling institutional knowledge. So on this next slide, we'll take a little bit of a deeper dive into those challenges and opportunities that we've identified over our kind of 3-year tenure in this project so far. So really, our opportunities for improving the dam safety program at TransAlta Centralia were getting these inspections focused on the potential failure modes. The regulator had stipulated the inspections to occur at a frequency, and the regulator was very comfortable receiving just a very broad stroke of inspection, a few yes or no questions, but really not digging into the details of what the failure modes were, why we were looking at certain things. So we wanted to revamp the inspection program to really get into those details, and so that we could start understanding dam performance at a deeper level. We wanted to decrease the time between observation and action, doing a lot of paper workflows, has the opportunity to introduce error at several iterations. So we're looking at going out in the field, we're collecting data on paper, we're coming back to our offices, we're transferring that data into a spreadsheet, and then possibly from there, we're even transferring that data to other stakeholders and consultants who are then transferring that data again into their own spreadsheets and looking at the data. So we're looking at 4 or 5 touch points for any given instrumentation data or inspection data that's coming out of the field. We wanted to look at ways to decrease the opportunity for errors to be introduced there. That also helped us to decrease the time. Validating the data, validating the observations in terms of, was the inspector at the correct instrument when they were inputting the data, and how much time are the inspectors taking on the inspection, are completing these inspections? Is it a 5-minute inspection of a dam, or is it an 1.5-hour inspection of a dam? Both ends of those spectrums can give us an idea of how detailed and in depth that our inspectors are understanding these dams. Distilling institutional knowledge. I think this is something that everyone suffers from. We see it in multiple projects where the project team has an intimate understanding of how a dam works and how it is inspected and why. But but a lot of that information is stored in our heads, and it's not well represented on paper in terms of being in our OMS manuals a lot of the time. Reporting efficiencies, automatically generating reports. This is a great way to gain efficiencies on a project. If you can get templates set up to spit out reports automatically, it's a great time savings and effort savings in terms of monitoring and inspections. Improving stakeholder engagement, that was another thing we focused on in this system. Really enhancing collaboration and communication throughout our project teams. A lot of the times on engineer of record jobs, we check in periodically and meet as a team. But this system actually facilitates that a lot better, and a lot smaller or shorter interactions occur more frequently. And just getting into continuous improvement, we always want to be moving forward in terms of our dam safety programs. There's never a point where we're going to, I think, be comfortable with how we monitor dams. I think we're always going to be striving for that next level to make sure we completely understand the performance of dams and get better at integrating that information and acting upon it. So in the next few slides, we're going to go through a bunch of the applications that we've developed for this site. The first one being a catalog of historical aerial photos. So what we've done is we've digitized and georeferenced many historic aerial photos, both from public sources and from TransAlta's records. You can see in this GIS-based tool here, we're able to swipe the images over top of one another. We've digitized a bunch of features on previous imagery so that we can overlay those features on newer images in terms of structural components of the area, structural components of the dams, water lines from previous ponds, those sort of things. As we're viewing it and overlaying it on different images, it's given us a really great understanding of how these dams are performing and why. So this can be really an insightful way of using information that we already have to really paint that picture of how a dam was constructed, where performance issues may be occurring, and really why that's happening. So this has been an incredibly helpful tool with no additional cost of getting the data. It's just using that historical data in a much more effective way. Amy talked about tailored inspections, where we're going in now and we're building these digital inspection applications based on the potential failure modes of each dam. And that is really critically important. We don't want to be going out and spending our time on inspections just completing a checkbox exercise. We really want to get into the why of the inspection and looking at, what are my early indications that the potential failure modes are advancing? What can I look for to determine if this dam is performing as it should be? We've developed all sorts of checks and balances in the inspection forms. A lot of the text that you're probably seeing on your screens is too small to read. On the second slide, I just want to highlight there is on the top of that inspection application, there's a blue area that is shaded, and that is actually the location and extents of a seep that's been identified. So within the application, There's no way of measuring the quantity of seepage coming from this area, but what we're doing is we're mapping the seepage extents over time to see if that seep is increasing in area or decreasing in area. So by looking at spatial characteristics instead of quantity of seepage, we can then start to put together an understanding of some of these features on dams that are harder to understand. In the third tablet that you see there, there's some red text. What we've done is we've actually built in trigger action response levels into these forms. So when the inspector is going out and making observations, they're getting that real-time feedback on the tablet, looking at, if they've made an observation and that falls outside of the normal thresholds, they're getting that feedback, asking them to check and make sure they've entered that number right. And that what that's doing is it's preventing, and I think everyone's done it, is when you take your observations, you go back into the office and you start looking at what the numbers and the observations actually mean. And then you think, oh, this is way out of normal, and then have to go back out in the field. This is taking away that step, or providing an opportunity to take away that step, where we're validating that data in the location, in the field, at the moment that it's being collected. A lot of validation techniques go into these surveys too, where we can show the location of where the observations and the data is being taken, so that we can validate that the inspector said he was at piezometer A, and the collection shows that he was at piezometer A, and so that we're verifying that that the data from the reading was taken on the correct piezometer. Also, the time that it takes to complete these inspections, I mentioned that before. Whether the inspection was just a quick overview of the dam or whether it was a more in-depth dive, some of that information is really important as we think about how well our structures are being inspected and how well our staff are trained in doing their inspections. Operations and maintenance log. This gets back into distilling that institutional knowledge. Some of the ponds at the TransAlta Centralia mine are being, the level of those ponds are operated with weir boards. And so temperature requirements for release prevent the release of water at certain times of the year on site. And so the dam operators, the pond operators, know when to let the water go and why, and how many weir boards should be set in the ponds to manage the water throughout the year. But none of that information was ever written on paper. So we've developed digital routines which allow us to extract that information out of the heads of the inspectors and get it on paper in a digital format, so that when changing of the guard occurs, we're able to impart that knowledge on to potential new staff in the future. Same thing with maintenance logs. We're using the inspection routines to distill maintenance items that we're finding in the field during these inspections into a specific dashboard that lets us dig into the maintenance items and track them from identification to completion. So we're tracking, identifying the items, assigning them, assigning resources, and implementing the fixes, the remediations for those events. It's been a really powerful tool to bring on board so that we can really understand how we're improving the processes on the site. We get into instrumentation monitoring. This was really critical for our pneumatic piezometers on the site. We've got a number of pneumatic piezometers which are not easy, maybe impossible to automate. So a lot of the instrumentation we talk about nowadays is vibrating wire sensors, which we can hook up to data loggers, and we can bring that information into our systems really easily. We often forget about our manual instrumentation that often is not going anywhere. We're not going to go in and replace a whole fleet of pneumatic piezometers just because we want more updated information. We're talking about drilling through dams, which you should have a really good reason to do. And I don't think that updating the instruments that are currently working is a sufficient reason. So we've developed a routine that allows us to capture this data through the use of tablet applications and then display it on a dashboard within the GIS software. Moving into INSAR data, I started working with INSAR data a number of years ago, and I was frustrated by the complexity of the data sets. It was really hard to work with and manipulate the data myself and in our larger project teams. Really, we were relying on a few key individuals within our organization that we were going to help us investigate and interpret INSAR data. When we started using this technology more widespread, those people's time became very valuable. And I thought, well, why can't we just develop a tool that can help our project teams get in and really work with the data and understand it? So we've developed some simplistic tools within GIS that allows us to create these project-based dashboards and look at INSAR data in a really easy way. That's helped us to get more eyes on the data in terms of our personnel and our clients looking at the data, providing interpretations and understandings that a single person is just unable to make. So really, we're increasing the value we're getting out of these INSAR data sets by leveraging really simple tools to get this data out to a wider network of people. And just a final slide here on data visualization. And this gets back into sharing the data, having these really collaborative discussions where a lot of benefit takes place on both ends for all types of stakeholders. Just being able to pick into a site and visualize it in 3 dimensions, draw cross sections, have instrumentation information, photos. We've used this to help orient new staff coming into this project, where, instead of just giving people reports to read, we're now giving them access to our GIS, and they're able to go in and look at things in 3D and really start to visualize what's happening on site. It's been an incredibly valuable tool in that respect as well. A lot of times our regulators aren't as familiar with the site as we are, and this really helps us to get ideas across to people that may not be as intimately involved in the project as we are. And really finally, just coming back to having all of our data in one place, being able to access it really easily by people remotely across the country. Our engineer of record, she lives and works in Calgary. The site is in Washington State. I'm in Charlotte, and we're all coming together in one central platform with access to all of this data in real time. Just a couple final slides on resource requirements and basic costs. all of these applications were built by GIS professionals. That includes people that just have an interest in GIS and are proficient with it. One of the great things about a GIS is you can build it a la carte. Some of the applications I showed here, they weren't all developed at once. You know, we didn't start the project with the vision of having all of these applications. They were built as add-ons to each other. We would build one application, which would start to generate different types of questions, and we would find and build another application to solve those questions, and it kind of just snowballed like that. So really, on average, we're looking at an application can be built and refined for $10,000 to $20,000. Annual software subscriptions for GIS systems are anywhere from $1,000 to $3,000 a year, and that's for a relatively small user group of 5 to 10 users. A lot of companies, a lot of our clients, a lot of consulting companies that we work hand in hand with, they already have GIS subscriptions, and this helps us to really integrate our data with the data from others. There's not a lot of proprietary stuff that goes on in a GIS, so transferring that information between parties becomes really simple and easy, which is another benefit of the systems. So we are really enjoying the technology and advancing it continuously as part of our dam safety programs. Finally, lessons learned. GIS is a powerful data aggregation and visualization tool. A lot of the data that we collect in the field has a spatial component, and what better way to display it than in a spatial-based software. We learned through the process that flexibility has to be maintained in the data collection strategy. As we first developed the inspection apps specifically, we really locked down a very structured approach to the inspections. And we found that didn't work very well. The inspections weren't being done in the way that we imagined they would be. It didn't leave the flexibility to change the flow of the inspection. And so in our second iteration of the project, we went in and we took away some of that structure and made it a more fluid experience. And that has really helped us gain a wider acceptance of the inspection applications. Again, going back to the INSAR analysis, simple applications can be configured to increase the accessibility of complex data. Really, really critically important in helping us to understand the whys of performance. Built-in data validation techniques and the interconnectivity between mobile devices and our internet-based dashboards for real-time data integration. This project has been a great success. It's helped our confidence in the data. It's helped us get the data in a more streamlined way. And it's really facilitated a great collaboration between us and the client. And that's it for case study 1. Thank you.
Thanks, Mike. So back to me for case study 2. Start sharing my screen. There we go. Okay, so case study 2 is the Springbank Off-Stream Reservoir project, which I'm sure some of you are familiar with, but for anyone who's not, it is a dry dam that is currently under construction just outside of Calgary and to the north of Bragg Creek in Alberta. To give some context, because I will be mentioning some of the names of the companies that are working out here, the prime contractor on site is Vinci, and Stantec are the designer of record and are also completing QA services on site. So Amy has already introduced a couple of the technologies that we're using on site, and this case study focuses on the areas of interest for me on Springbank. I'm the instrumentation lead, sorry, during construction. And as you can imagine, the things I'm going to be talking about today involve instrumentation, but also construction monitoring. So starting with construction monitoring, similar to the system that Mike described for Centralia, we've also adopted Survey 123 to develop field forms for use on the project site. So our field review, all field reviews that are completed on site are completed using these forms, and we've developed different ones for different teams. So right now the earthworks and structures team share a daily field report. Our Indigenous monitoring team have a separate report that they use for any chance finds and to make any observations on site. Our geologists are using forms for foundation mapping, technicians for compaction reporting, and our environmental scientists, similar to the Indigenous monitors, are using it to pick up any environmental observations on site. So to kind of talk through the reporting process a little, during inspection, all of our field crews are equipped with iPads. And as you can see here, when we go out to site, we have our iPads ready. And similar to the system Mike showed, it prompts us through all of the observations that we should be making out there. So we have prompts asking for the details that are needed. Photos can be incorporated into these forms, so we can take a picture of any observation, say for example the rebar that was being reviewed during that inspection. If there was an area where the spacing wasn't quite right, a photo can be taken, but then annotation can also be done on that photo live in the form. I think, once the inspection is completed, the report can then be uploaded to our dashboard, which can be seen here. And as you can see, all those little orange dots, that's geo-referencing all of our inspections. So the key benefit with this is that the field review forms can be submitted right away and with no delay, as all of our iPads have cellular service. The dashboards show where all the reports were completed, but more importantly, it gives all the details that are submitted as part of that report. And that really gives us integrity of reporting, because then the observations can be tied to a specific point on the project site and a specific time. The office-based design team has access to all of these reports and can review them right away as they're submitted from any location via a browser or on the project app. This allows the project team to respond quickly to any reports that don't contain enough information, or if any issues with construction are identified, then that feedback can be given right away without any sort of delay that you would expect if you were scanning and uploading traditional paper-based forms and then uploading individual photographs, which does take a bit of time to process. So all of this goes right away and we can respond to it and take any remedial actions if needed. So the forms have been continually updated as the project has progressed to reflect the changing needs. So in this case, when we first mobilised out to site, it was only the earthworks team that were present. So our field review forms really had a soil flavour to them. When our structural team mobilised out to site, we then recognised that we had to update the forms to meet their needs and started incorporating things like rebar checklists. Once the inspections are complete and the forms have been reviewed, they can also be easily exported to a PDF format that we have specifically designed to meet the project reporting needs. And we can then provide these reports to the client to meet the daily reporting requirements as part of our contract. And they can also be incorporated into the construction completion reports to meet the requirements of the Alberta Dam and Canal Safety Directive. Okay, so on to instrumentation. As you can imagine in a construction site, our real focus with the instrumentation program out here is the short-term monitoring during the embankment placement and also in the diversion channel excavation to confirm that the performance is in line with design and to confirm slope stability during excavation. After handover of the structure to Alberta Agriculture and Irrigation, the instruments will then be adopted for long-term monitoring. And just to give you an overview of what we have on site, there are 6 instrumentation sections within the diversion channel and 9 sections within the embankment dam, both of which include instruments designed to monitor pore water pressure and deformation. And then all of the instruments are either linked or are being linked to an ADAS system to allow for real-time monitoring. Okay, so that being said, what have we actually installed out on site here? So in the diversion channel, we have vibrating wire piezometers or VWPs to monitor for pore water pressure and SAAs to monitor for lateral deformation, both of which could be indicators of a stability issue that poses a risk to construction workers or equipment that are present in the diversion channel base or within the diversion inlet during construction. In the dam construction zone, similar to the diversion channel, although we're monitoring for slightly different reasons, we also have vibrating wire piezometers. In this case, we're monitoring for excess pore water pressure during fill placement, and also shape accelerators to monitor for possible developing stability issues as the dam construction continues and we reach higher elevations during construction. In addition to those two, we also have vibrating wire extensometers and vibrating wire settlement plates, both of which are monitoring for vertical deformation or settlement during fill placement. All of the current instruments that we have on site have been placed within the dam foundation, and as construction proceeds, instruments will also be installed within the dam fill. And as I mentioned, all instrument sections are linked to data loggers, which transmit to the site communication hub via radio and then ultimately to the project ADAS system. Okay, so the project ADAS system that has been selected by Vinci for use on the project is beyond monitoring by Sixth Sense. As you can see here, it's similar to the other data management systems in that it's taking our data from site and presenting it visually on a dashboard. The ADAS system is currently in the preliminary stages of launching, with only the data from the instruments being available for review right now. But we are working with Sixth Sense to update this system to meet our project requirements. And in the near future, we'll be seeing things like instrumentation elevation and fill elevation on the VWP plots, for example. As well, an interactive plan will be added similar to the system that Amy showed earlier when discussing Canary, which will allow us to have a 2D overview of the site, be able to click down and look at areas of interest. So for example, if I know that fill has been placed on section D11, I can focus on that specific instrumentation section and look at information from the instruments on that alignment to monitor for the response there. Alarm levels have currently been set for the shape accelerators, which will send automatic text messages and automated phone calls to key members of the Vinci construction team. And that allows us to react to any possible signs of stability issues and to react accordingly with Vinci's health and safety team out here. We're also currently developing alarm levels for the VWPs at the moment so that we can get similar notifications during construction in case we have to take any action in terms of the volume of fill being placed or the rate of fill being placed. It's also very useful to the contractor and not just the geotechnical engineering team out at Springbank. As you can see from the dashboard, you do see key stats on the reliability of the instruments that have been connected to the ADAS system. And this really assists Vinci with their preventative maintenance, as all device health can be monitored from ADAS. And then any repairs can be scheduled ahead of any possible loss of data or loss of transmission of data occurring. And we have had some teething problems with some batteries on site, and this has been fundamental in making sure we don't have that data loss, because Vinci can react to low battery levels very quickly. Okay, so that being said, we have all this amazing data coming at the design team and at the construction team here, but what are we actually doing with it? So the live construction monitoring data is being used by the design team to confirm that the construction of the dam and the supporting structures meet the design intent and performance criteria. So the instrumentation data collected during construction is crucial to confirm that the analysis completed at the design stages of the dam has accurately predicted how the soil foundations are going to behave. The live data from the instruments will be used to assess the foundation performance as fill is being placed and allow us to make decisions about fill placement. So if we see optimistic responses in the ground, it means we can allow more fill to be placed over a shorter period of time, or perhaps if things are not performing satisfactorily, we would slow down and allow pore water pressure to dissipate. So really having that live data is key for us to make decisions on site. The stability of the dam will also be monitored as construction proceeds via the SAEs, as I mentioned before. And again, having that live data allows us to appropriately respond to the readings that we're receiving. Long-term, the instrumentation is going to provide key information, because when you're constructing a dry dam, we don't get to have that first filling test, and really the first time the dam is going to be tested is during the design flood event. So using those instruments to monitor how the dam performs during that first filling is going to be really key for the operator. Looking longer term, the key instruments really will be the VWPs and the SAEs that are installed within the dam to allow continued monitoring of the stability and pore water pressures, with the VWEs and the VWSPs taking a lesser role. The diversion channel instruments will continue to be useful in monitoring the continued stability of those slopes, but again, they're not going to be quite as important as the VWPs and SAEs within the dam structure itself. Okay, so I do want to touch a little bit on the cost of applying the advanced technology, but it would be really disingenuous for me to present the cost from Springbank, because we are only part of the way through the project. And because of the way the contract has been broken down, it's really difficult for me to bring out the costs of individual components on the site. So I'm going to be focusing on my experience and application of some of these systems in Alberta in general to provide some idea of costs. So the Survey 123 forms were developed using existing infrastructure available to Stantec staff, so there was no need to build a background database to power our forms. So it took us very little time to create and update those forms. Our staff also utilised pre-existing equipment such as iPads and iPhones. But that being said, the cost to set up a similar system with just field reporting forms and a dashboard, we're currently completing for an Alberta client with our digital practice team, and that cost is at around $40,000, excluding equipment costs. One of the nice things with Survey 123 is that it is Android enabled, so you can buy tablets relatively cheaply to support this system. Moving on to instrumentation, the advanced instrumentation costs are in the order of 2 times the cost of traditional instruments, just roughly as a breakdown. So perhaps if we'd installed SIs versus SAEs. But one of the really interesting things out at Springbank is there was a period of time between the commissioning of the instruments and the commissioning of the ADAS system, which meant that we were having to manually download from all of our instruments for a 5-month period. So that gives some insight into the amount of time that it takes to actually download readings at one discrete data point. And in this case, it was taking a staff member an entire day to get around site, download the data, and that's not taking account of the processing time afterwards to be able to manually plot, for example, the VWP data outputs. And then if we had installed SIs where it's not a case of simply plugging a laptop into the SA and downloading the data, again, I think that could have easily been a 3-person team taking 1 day to download data. And if you apply those costs over the duration of this dam's life cycle, not just the construction, I think you really start to recognise the value in installing the advanced technology and having that upfront cost, because you're going to see the savings in future. And additionally, having one discrete data point out here really wouldn't have been good enough for us during construction monitoring when you look at how we're applying the technology. There are also costs associated with commissioning the ADAS system. And again, that's really going to vary based on complexity. And I did forget to mention that with the Survey 123 forms. In both cases, the complexity of the system that you want to have for your project is really going to drive the cost. If you're getting more complex and need more complex output, there's obviously a cost associated with that. There is some ongoing maintenance required to run the system out here in Springbank, and that includes the replacement of desiccant within all of the data logger enclosures, the cellular costs for the operation of the communication hub, ongoing licensing fee with Beyond Monitoring and with Survey 123, and possible replacement of any damaged instruments. And aside from the licensing and the cellular fees, these are the kinds of costs that we would see even if we were using traditional instruments on site. So lessons learned from our first year of construction. With the construction monitoring forms, as I mentioned, we did have a couple of revisions made to those. And I think we maybe could have put a little bit more planning into that up front so that we didn't have revisions. Ultimately, the revisions took very little effort to do, but it's something I would consider if I was applying this system on another project. Also understanding what you're actually going to use a field field review forms for and what kind of output you want to, because you can really tailor that form to match the output you want. Ours fit very nicely with the PDF system, but I'd encourage anyone developing a similar system to think, what's the end product? What's the end goal that I would like to get out of this? With the instrumentation program, our lessons really came purely from procurement for a couple of items. With coming out of COVID-19, there were some supply chain issues around the data loggers that had originally been specified for the project. Thankfully, there were alternates available on the market that we were able to approve, but if we had to wait for the data loggers that we had originally specified, I believe that would have been up to a 6-month delay to be able to get those to site and then be able to install. Due to the instrumentation lead times as well, which for an SAA back when we were first ordering the products was around 6 to 8 weeks, the instruments had to be ordered prior to drilling to meet the overall project schedule, which meant that when we were actually advancing the boreholes, some of them had to be drilled slightly deeper to meet the project requirements and some slightly shallower due to varying bedrock depth. Thankfully, because some were longer and shorter, we could switch the SAAs around and had some flexibility out on site. But we did have to order 2 brand new instruments, which again led to a slight delay because of that lead time. And if we'd had a little bit more time in the schedule, it would have been great to be able to drill those boreholes and then order the SAAs. And as I mentioned in the last slide, there was a slight delay between instrument installation and the ADAS commissioning, which meant that the instruments were manually downloaded for a period of 5 months. And we did lose data on days where there was heavy rain, as the light duty vehicles could not access all instruments. And thankfully this was occurring at a time where it was mostly stripping and things that was occurring on site, so it wasn't key to get the real-time data. And thankfully now coming into the second year of construction, we're getting all of the data that we need in advance of the dam being constructed. And that's all from me, and I'll hand back to Amy.
Thanks, Amy. Let's get my screen opened here. Okay, so the third case study I'm going to present is the development of a digital monitoring for a small dam owner. And I really I found this really practical for, I think, a lot of dam owners that may be not using the most or a lot of advanced surveillance techniques, or may not have a digital database started. And we presented a lot of advanced surveillance techniques today that I think can be, oh, wow, this is everything that's available and I'm back here. And this is kind of a little bit on how you're going to get into those first steps, similarly to what Mike presented in the first case study. So just a bit of a project owner. The client was a dam owner in Alberta that owned 395 stormwater facilities. And within those facilities, there was approximately 150 small dams with a consequence classification according to CDA guidelines ranging from low to high. The dam safety management program was in its, to say, infancy stage, where they were recently developed a new dam safety monitoring plan. Surveillance records were limited, where some records were paper copies, some records were digital copy, and some inspection records were maybe not recorded at all for routine inspections. So what we were able to do, we were really able to leverage some technology to really help development the dam safety management system. So to really help get all the records together in one place, to help with the staff training, and also keep those staff training records, to aid in the surveillance of these dams and the recording of the surveillance information. So the objectives and scope of the work. So the primary objective of this project was to really develop a single place to maintain all the design, construction, and dam safety documentation. With approximately 150 dams, that's a lot of information to manage in a lot of different places. So we really wanted to get that into one place. So if you're going to do a dam safety review or inspection, you could get all the information in one place and it would be right there. If an issue came up or if you're out at a site, you can again pull up that information in one place just to make getting that information that much easier. One thing that was really recognized when we were outlining the scope of the work on the objectives objectives is that we really needed to have a strong collaboration between the owner and the Stantec ArcGIS team. We were doing this as a collaborative approach. We were really trying to meet the owner's needs, work with the existing IT that was available, because we were going to be working with us and doing handover to the owner down the road. It was also identified that we had to utilize an interim database. So knowing that it was going to take time to develop the full database and have that fully operational, we needed to start working on getting these interim records all together in one place, develop this and then so down the road, we could have all the interim database imported into the long-term operating database. And then we also wanted to develop a digital inspection form, and with that, the automatic inspection reporting tool, similar to what was shown in the first two case studies. Also wanted to develop that document management system, and then to put it all together and make it really functional, have that operations dashboard. And then one thing that I want to again note is that the owner really recognized that this was the starting steps, and they recognized that the scope would really be expanded for continued development. Like we discussed in the early introduction slides, that your surveillance system should be continued improving. So this is where this was the starting point in getting those initial steps, but identifying that over time, they're probably going to add additional modules, as Mike had explained in the first case study. So the methodology to really meet the objectives and goals of the project. So there was, of course, the data storage, and then the operational use. So for the data storage, we wanted to get the background documents into the asset database, as well as the inspection database together, feeding that asset database. And then of course, there would be the development of the mobile inspection and reporting tools. We took advantage of using the existing online GIS system that the owner had. So they already had that existing GIS system, and we wanted to work with that and the existing GIS team to capitalize on that and reduce costs, and have only one online platform for operations use. So with the data storage, how are we going to actually use the data storage to reduce the risks in the dam safety management system? We would have the information, then we would have the offline data analysis for interpretation. There would also be other analysis, but then we would work on building the dashboards for inspection review, and then also for operations and maintenance tracking, which would help to aid in those decision-making tools. So this is just a screenshot of the interactive dashboard that's in development. And so on the sidebar, you would have all the available dam assets, which are organized by their classification type. You could click on what classification you would like, and there would be a drop down with all the dams named. The GIS coordinates are spatially labeled and color coordinated by classification. So all the red dots represent a high classification structure, and the orange dots represent a significant consequence classification structure, and there's other colors involved as well. So the interactive data management, as I mentioned, one of the primary objectives was really to get all that documentation in one place. So on the point and click method, you can click onto a particular dam, and you would have this option pop up where it would have all the available background information. So you have the option to look at background drawings, background GIS files, models, pictures, and then reports. And then if you were to click on background drawings, again, it would just pop this up, all the available drawings that are available, and you can open them up. So you can imagine just what a useful tool that would be if you're on site and maybe you didn't have drawings printed out, or a feature popped up that maybe you weren't planning to look at. You could just open up the database on your phone or tablet and be able to pull up the relevant information that you needed right there on the spot. So the field inspection form. So this is in development, but we're currently going from paper to paperless. So we actually use the existing field inspection form that the client was using to carry out all their inspections. And we're just working on building and developing that digital inspection app that's similar to the inspections that were used in the first couple case studies. And then it's going to be, like, again, understanding that it's a work in progress for, we're starting with one inspection app, but it can be tailored into for specific dams if you need to implement additional items to look at. It's fully flexible. So this is what we're working on now. So some costs and considerations. So this is a work in progress and the development of the database is still ongoing. But it can be understand that the data management system and the development, if you maybe don't have something electronically started, it can be really overwhelming when you have multiple documents that are stored in different places or on different files. Maybe you have a lot of design documentations that haven't been digitized yet and they're just in a hard copy or print information. It can be really overwhelming on where to start. So if you are going to implement technologies, it's really critical to ensure, just like with any dam, you have to have a strong foundation and then work outwards using a phased approach. You really have to have that strong backbone to have a successful monitoring plan. You really have to understand your risks and your objectives. And it's better to start with those smaller steps rather than incorporating all this advanced data and then not knowing where to exactly put it. Again, it has to have a really strong collaborative effort between the owner and the consultant to make sure that all those risks are managed and you're getting, you're working on building the program to meet all the objectives and scope to really minimize those risks. It has to be observed that it's going to take time to implement. So the current project that I discussed today estimates a 3 to 5 year period before complete handover to the owner. And so understanding that we had the consideration of the interim database and just understanding that it's going to take a bit of a longer period to implement, but that reward will be used and noticed once you have all those documents in one place with the quick ease of access. And then it's also good to anticipate further development beyond the scope, as mentioned a few times throughout this presentation. Surveillance programs should be fully developed along with technology, but along with other issues that might be identified with the dam. And it should always be a continuous improvement circle. So for this project, the initial implementation costs were estimated to be approximately $100,000. But the initial, I just want to emphasize that the initial implementation costs are really dependent on the scope and the objectives, how you want to use that technology and what you want to implement, and then of course, the amount of data that you're going to be using. So just in reflection to wrap up today's webinar, monitoring and surveillance technologies are continuously improving. There's advances in technology that are happening really rapidly. And so there's a lot of new tech tools and technologies that we can be using. These recent data management technologies can really help to organize large amounts of data and present them in a really user-friendly visual format to simplify interpretation. And maybe you might even, using this new format, you might start interpreting data or looking at things that you maybe haven't in the previous 30 to 50 years of the dam's history. There's recent topographic technologies that are available that can really help develop detailed elevation models, and they can really help in any modeling analysis and review of deformation. There's been instrumentation advances that really help to create increased resolution in the monitoring of pore pressure and deformation monitoring. So dam safety specialists can really incorporate these advanced surveillance techniques into monitoring programs to really help to reduce uncertainty and thus also the risks of potential failure modes. As stated a few times, we want to develop all surveillance programs in alliance with the CDA principles, reducing those risks to be as low as reasonably practical. And you need to ensure that you have the right tool selected based on your surveillance needs for the given structure. Just like in the medical profession, you wouldn't want to go see a doctor and have them complete an X-ray if you're complaining about a stomachache. You just have to make sure that you're using the right tools for the right purpose. So with that, I think that takes us into the second question session.
Okay, thank you. So we only have a few minutes here for Q&A, but the panelists have been answering questions, providing text responses to the question. So if you don't get to your question, maybe check there now in the answered section to see if an answer has been provided. So Amy Snedden, this question's for you. Are there any VWPs fully grouted at Springbank? Do you have a baro sensor on site to be able to partially barometrically correct if you see a baro signal in any of the fully grouted piezo's?
So they are all fully grouted. We don't have a barometer on site for the VWPs, but the VWSPs are being corrected, or the readings from those are being corrected with barometric readings. Right, that was an easy one to answer.
And here, maybe we'll follow that up with the next question here. What sort of surge suppression precautions have you used?
So we do have lightning protection on each of the instrumentation cable runs that we have on site to protect the instruments.
Now, there have been quite a few questions about SAA versus SI and good applications for SAA. Can you speak a bit more about or recap what applications are best suited for SAA?
I think it really comes down to what data you need to be getting from your site. In some cases, like I kind of mentioned while I was talking during my slides, if you only need discrete monitoring, then yes, for sure, stick with the traditional SI. When comparing that, I think there were some questions around the in-place inclinometer versus the SAA because they're quite similar products. And to me, it's a case of making a judgment yourself as an engineer because they are so similar. The SAA is a product that I'm really used to and have applied in dams across Alberta, but that's not to say it's better than the IPI. And it's really about understanding your specific needs and what information that you want to get from your instruments, which I think is a very common theme of the webinar, is making sure that you're not applying technology needlessly. You're applying it in a smart way and to meet your needs.
Okay, thank you. Now, what sort of this? I think this question might be able to start the response. What surveillance techniques are most appropriate in remote areas where there's extreme environmental conditions?
Yeah, I mean, there's several remote sensing techniques that are great for that, Jenna, and I posted a link in my answer to the question online, but there are some great drones coming out which are able to be operated remotely. They live in little docks and they'll come out and do a flight at the click of a button or on a schedule. And INSAR is only one of the satellite-based remote sensing techniques that are out there. There's a lot of other applications for satellites, photogrammetry. You can look at different image spectrums, vegetation health, all sorts of different things in that regard. And soil moisture as well can be done remotely. So looking for potential seepages on dams, that can be also completed with remote sensing techniques.
And here's another question for you, Mike. How have you dealt with line of sight displacements with INSAR? The line of sight displacement that comes with INSAR. Sorry.
That's a really great question, and we're working with a lot of our vendors on that right now. Is understanding the interpretation of INSAR data is not very cut and dry, and the results that are provided by the companies that do that often come with little or no context. So getting the data is just the first step. That interpretation piece, really, we need to advance that as an industry and ask more of the INSAR providers, because really you've got to navigate your how the satellite is looking at the topography, what the topography is doing in terms of slope. data moving away from the satellite can be interpreted 180 degrees differently depending on whether you're sloping towards the satellite look angle or sloping away from it. So there is a lot of nuance that we still don't understand fully in INSAR data. I was talking to a colleague yesterday and we were talking about, really INSAR right now gives us a binary look. Is something happening? Yes or no. That's really all we have at face value. It takes a lot of work to dig further into the data to really interpret what's going on. And that's something that we're not doing as often right now.
Okay, one very last question. This is for Amy Sweard. For the City of Calgary GIS system, does the GIS link to an existing file system, or have you established a parallel file system in the GIS?
Yes, so I'll admit that as the geotechnical engineer, I'm a little less in the loop on what the GIS team and the I team is doing on this project, but because it was an interesting project, we still wanted to present this. Mike can maybe speak to this a little bit more, but I believe that we're right now, as we're in the development stage, we're just working on building something in parallel. I think we still have to, we're still in the early phases, so we still have to link to, for that initial background, how we're going to back it up, and then how it's going to sync in the long term.
Yeah, that's correct. So right now we're starting small with developing the GIS system for this specific client, with the overall goal of eventually having everything incorporated into one system. So it kind of goes back to the way Mike was talking about Centralia, where we're taking baby steps towards ultimately having that one tool that's used to monitor everything.
Okay, and thank you. That brings us to the conclusion of, sorry, we're wrapping this up very quickly here. It is the top of the hour. I thank our presenters today. I thank you for joining us. A short survey will be sent out. Please do complete it. It means it really helps the CDA develop these workshops and this programming. The next webinar in this series is on February 22nd on the detection of seepage using non-destructive techniques. So again, sign up for that one. And next week, next Tuesday, is the deadline for abstracts for this year's annual CDA conference. So if you are preparing that abstract, finish that up, get that in. You have a weekend if you're still interested in submitting something. There is still booth left, and yeah, join us then. Thank you. See you next time.